Hi everyone. Thanks to all of you for coming today. So I'm very excited that today we have Mike Kim as a speaker. So Mike is a postdoc at the Miller Institute for Basic Research and Science at UC Berkeley, where he's advised by Shafi Goldwasser. And before this, he got his PhD from the Stanford Theory Group, where he was advised by Omer Reingold, who's actually the director of this whole TOC4Fairness initiative that is right here. So Michael has done a lot of great work actually on the foundations of responsible machine learning and on algorithmic fairness. I'm sure you've heard a lot about multi-calibration. Well, you can thank Mike for this. Another very important piece of trivia about Mike is that if you write Mike Kim backwards, it's still Mike Kim. If you follow him on Twitter, you probably already know this. So anyway, I'm very happy to have Mike as our speaker today. So yeah, take it away, Mike.
Thank you for that introduction. Great, and so thanks all for coming. Today I want to tell you about some of our recent work on outcome indistinguishability. It's joint work with Cynthia, Omer, Guy, and Gal, many of whom are on this call, and it's going to appear at STOC this year. So really, truly, I hope that this can be interactive. I hope that people interrupt me. So please unmute yourself. I would much rather have people unmute themselves and interrupt me and get through 40% of my slides than get through all of them very quickly and have nobody understand anything. So please let's have it be interactive. Great. So let's see. So these days, I probably don't have to tell this group, but these days predictive algorithms are everywhere you look. They're driving our cars, they're making medical predictions, sometimes even telling us who we should get married to. And increasingly, these algorithms are having a really profound impact on our daily lives, making consequential decisions about people. And so while such predictive algorithms have the potential to yield great benefits to society, for every amazing algorithmic achievement you hear about, unfortunately, you also see headlines like these highlighting the unfair discrimination and bias that can be baked into these predictive algorithms. So amidst lots of concern about bias in algorithms, it's easy to identify situations where we see an algorithm and it's behaving in a way that somehow we feel is unfair. But coming up with a systematic and formal way to mitigate algorithmic unfairness is quite a bit more challenging. And that's, I think, really where the work of this group comes in. And it's a great program. And I want to talk just at a high level about how I view the goals of this program. So rather than addressing each example of bias and unfairness as we discover it on the fly, really, I view the goals to be to observe patterns of unfair behavior and translate these patterns into formal notions of fairness that we can reason about in the language of theoretical computer science. For me, probably the most important part of this work is focusing on the definitions and making sure that we have the right definitions, balancing the need for general purpose solutions, as well as an awareness for the context in which the definitions will be applied eventually. And really, ideally, the definitions that we come up with will help to clarify what we can and cannot expect from machine learned predictors. And so I think that is squarely where the work that I'm going to talk about today lies, is sort of in proposing a definition and seeing how it helps us understand what we can expect or what we can insist of predictors that we train in practice. And so the eventual goal of the program is really to develop provable, efficient machine learning that comes with a certificate of fairness, much in the way that modern cryptography has developed to be able to give us a provable certificate of security in our browsers, let's say. Good. So now zooming back into today's talk, what do I want to talk about today? Well, I want to motivate with sort of a toy example or a toy setting where, say, a patient is coming into the clinic and is maybe worried about the risk of disease in their family. So what will they do? They'll go into the clinic and the clinician will record some features of them, record some health factors, put them into some vector. We'll call them covariates or features. And then the doctor will enter those into a program, a predictor algorithm. And this predictor then will spit out a score, let's say 0.6, which will be understood to be the risk of cancer in the next 10 years, let's say. And so popularly, this score, this score in the interval 0 to 1, will be understood to be a probability of the outcome. So the probability that this patient, this individual, will develop cancer in the next 10 years. But what can such risk scores really mean? For instance, concretely, in 10 years' time, the patient will either have developed cancer or not. And unlike many other events that we like to reason about in a probabilistic way, we can't simply rerun this experiment. We can't say, run back 10 years, patient, and see again and see whether you develop cancer. This event that we're trying to predict about this individual is inherently unrepeatable. And so the sort of broad overarching question that we want to revisit in this work is, what is the probability of an unrepeatable event? Now, this is a huge question that's been studied in statistics, philosophy, probability theory without obvious resolution. And I don't pretend that we're going to resolve it today. That's probably beyond my pay grade. But what I am going to try to do is convince you that the computational perspective here is interesting and is useful. And so we're going to propose a new interpretation of this question that hopefully will shed some light on what we can hope and what we should insist of algorithmic predictions. Good. So the plan for the rest of the talk is to overview some classic views on risk scores and individual probabilities, and then introduce our notion, outcome indistinguishability. And we'll see that there's actually a variety of flavors of this definition that we can talk about. Then we'll talk about how to achieve OI and show some connections to this work on evidence-based fairness. Then we'll show, time permitting, we'll show a lower bound for achieving OI based on fine-grained complexity, and we'll discuss some broader implications of the work. Good, so I'll take a quick pause, but I'm guessing there aren't too many questions yet. Good, so what is our high-level setting? We're going to use a pretty common sort of learning setting, where we imagine that there's a population of individuals, which we'll denote by X. And for each individual, there will be some associated outcome, a binary outcome, that we'll denote as plus or minus or 1 and 0 interchangeably. And so the question that we want to ask is, given a new individual, maybe we see a bunch of historical outcomes of individuals and outcome pairs. And then we want to say, given a new individual, what's the probability that their outcome will be positive? And so really we want to understand this idea of probability and get a better handle on what this can really mean. Good. So perhaps the most standard approach to this kind of risk score estimation goes as follows. And many standard regression style algorithms work in essentially this way. The first thing that the algorithm is going to do is partition the set of individuals into a small collection of groups or types. So for instance, in here, I've partitioned it into 3 types. Maybe you partition it based on your features in some simple way. And then how will we derive a probability from this? Well, the probability of the positive outcome will be defined as the within type frequency or the within group frequency. So for instance, in this group here, if I've done my math right, then we count up and we see that there's a total of 12 individuals and 4 of them are positive. So perhaps the risk score in this group could reasonably assign a 0.33 as the score, as the probability. So this approach gives us a well-defined notion of frequency-based probability. The drawback, of course, is that the predictions, the probabilities that we obtain, are somehow necessarily low precision. What do I mean by this? Well, the repetitions that we get in order to be able to interpret this as a frequency occur based on grouping people together. So, for instance, at the extreme, if we only got to see one individual in each group, then the frequency-based approach really kind of fails. We're saying that this is an unrepeatable event. So then all of the probabilities would just be in 0, 1. It's not entirely clear how to interpret that. On top of sort of accuracy or interpretability concerns, there's also a concern that I've been calling algorithmic stereotyping, where every individual in a large group of individuals gets treated exactly the same way, right? So in this approach, you necessarily have to group a bunch of individuals together and give them all the same probability, right? Everyone in this group, we said, had scored 0.33. And this leads to a real sensitivity to the groups that you choose. So for instance, looking in this example that we had before, perhaps we want to reason about an individual in this part of the universe. And using the groups that we chose originally, then we would say that, oh, their score is 0.33, and maybe we think they have a low probability of positive outcome. But if I simply redrew the groups, if I chose a different set of groups to partition the individuals into, then all of a sudden, maybe this individual would appear to have a very high probability of positive outcome. And so this, what this is saying is that somehow the groups that we choose, the regression technique that we use, really can influence significantly our sense of probability for a given individual. So, for instance, if this was being used to screen patients for a risk of cancer, then in this interpretation, they maybe would not make the cutoff. But in this interpretation, they very much would and would be deemed very high risk. So there is this sensitivity to the groups that we need to be aware of in using this approach. So given the sort of uncertainty regarding an individual probability in this group-based framework, we might hope for a more sort of individual-based notion. And so one such notion would be to posit that every individual has some true probability of positive outcome. So in this view, we'll think of it's nice to think of sort of there being some all-powerful nature who's really calling the shots. And so what will nature do? Well, nature will do, for each individual, nature will select an individual level probability, which we'll denote as pi star. And then nature will sample each individual's outcome according to the Bernoulli distribution of pi's with parameter pi star. So the true outcome, which we'll denote oi star, will be sampled from this distribution. And so this is a very appealing framework in the sense that now we really can talk about an individual's probability of positive outcome. And so these probabilities are well specified by nature and give rise to a natural joint distribution over individual and outcome pairs. The problem, of course, with this view is that we can't really hope to recover nature's model. Just because we assume that these true probabilities exist doesn't mean that they really do. And further, it doesn't mean that we could ever hope to get our hands on them. And so without really strong restrictions on the way that nature behaves, this interpretation on its own doesn't seem to shed light on how we should interpret the output of an algorithm. Doesn't shed light on how we should interpret these algorithmic probabilities. So I want to talk a bit about what I mean by, or how this argument goes that recovering nature is impossible, because I think it sheds light on the next perspective that we'll give. So what do I mean by this? So the argument sort of goes, imagine that you're observing samples. You're observing individual outcome samples, and you get to see individual outcome pairs over and over again. The argument that it's impossible to recover nature basically goes by a counting argument and says, like, imagine that you are this observer or distinguisher, we'll call you, and you see an extraordinary number of samples, and you run for an extraordinary amount of computational time. Even after all of this processing, you still won't be able to tell whether your samples are coming from, in this case, green nature or the alternative yellow nature. So there are multiple consistent possible choices for nature. So you could never hope to recover nature precisely. You could never hope to recover the true parameters precisely. And so in this view, this indistinguishability of these two natures is viewed as a negative result. It's saying that somehow, even if we take an unreasonable amount of data and an unreasonable amount of computation, still we won't be able to pin down nature. But I think there's also a more positive spin on this impossibility. And it gives rise to a computational perspective, which says, in the real world, our analyses are actually reasonable. They're using a reasonable amount of data, and they're using a reasonable amount of computation. They're using bounded amounts of resources. And so the question we should ask is not whether we can recover the true nature, but can we recover a model of nature that looks like nature for all intents and purposes? For all analyses that we would ever run on this data, can we hope to learn a model of nature that would recapitulate the behavior of these analyses? And so this gives rise to our notion of outcome indistinguishability. So I'll be formal later, but for now I want you to sort of just have an intuitive notion of what it means. Outcome indistinguishability is a condition that we require on a probabilistic model. And what does it say? It says that the outcomes that are generated from this probabilistic model should be indistinguishable from those that are generated by nature. That they should be indistinguishable to all efficient distinguishers. And we'll talk exactly what we mean by efficient here, as well as what we mean by indistinguishable. But in a sense, we want to learn a model that generates samples that look like nature's samples. Good. So to tell you exactly what I mean by indistinguishable, we need a little bit of notation. So recall, you already know that we're denoting individuals by I in X, and their binary outcomes as OI in 0, 1. We'll say that a predictor, P tilde, is a mapping from individuals to the interval 0, 1. Tatsu, go ahead and interrupt me whenever.
Oh, sorry. Yeah, you were in the middle of a spiel, so I didn't really want to cut you off. But I'm curious about, in the previous section, much of your discussion seems very closely related to like the fundamental sort of problem of causal inference, right? Like you don't observe both outcomes and you can't replicate sort of, you know, a person's life trajectories, right? And so I'm curious about how this notion of computability relates to that question, because they seem sort of tightly coupled. Like if I put this,
I see,
the same question of like, you know, I want to do causal inference with heterogeneous treatment effects, it seems very related to this question of like, what is P? At which point I wonder how your framework sort of fits into that interpretation or worldview, or if you have any sort of high-level thoughts on that.
It's great. I think this all of these words that you just said are others have asked me nearly exactly the same question about causal inference and about heterogeneous treatment effects. I think it is very related. The important thing to note about what we're talking about today is that everything I'm talking about is observational. Everything here is observational, and I'm not claiming to try to come up with a treatment effect. There's no doing. I'm only talking about what can be observed observationally. And I still want to reason about a probability, let's say. But I think if you stare at it the right way, then you can, this probability need not really be a probability, it can be a score, and this could easily stand in for a conditional or overall treatment effect. So I think that's a great intuition, and I think you'll see that hopefully you'll agree that this will give you some good heterogeneous regression behavior.
Okay, I'll wait for the punchline then.
Yeah,
That's
great. Good, great. So we're talking about indistinguishability, and we're talking about sort of how our setup and how we're going to define indistinguishability. So good. So really the two objects that we need to reason about in this talk are two different distributions. One is going to be nature's distribution that we've talked about. This is the true joint distribution over individuals and outcomes. And we'll denote it as this DNAT star. And it will be a sampled individual, I, and a sampled outcome, which we'll denote as OI star. And so this is the true joint distribution over individual outcome pairs. Good. The second distribution that we need to reason about is a distribution that is induced by a predictor. So the observation is that every predictor, every mapping from individuals to the interval 0, 1, induces a generative model for outcomes. And so how will I generate a sample for an individual? Well, the first thing I'm going to do is sample an individual from nature's marginal distribution over individuals. So I'm not going to touch the distribution on individuals. But what I am going to do then is I'm going to throw out nature's outcome, and instead I'm going to resample nature's outcome. How will I resample it? I'm going to look at the score, the probability that my predictor assigns to individual I. So P tilde I is denoting this predictor evaluated on individual I. I'm using this subscript notation instead of parentheses, mostly just to avoid too many parentheses. So the point is that I'm going to resample this O tilde I according to the Bernoulli distribution specified by my predictor. And I'm going to output that sample instead. And so the question is whether a distinguisher can tell the difference between this distribution, nature's distribution, and the induced predicted modeled distribution. Good. So I'm going to keep going with sort of an intuitive overview, but if there are any questions about like the definition of this distribution, please interrupt me, because this is the most important part of the most important technical element of the talk. So instead of working with, instead of thinking about this indistinguishability of multiple natures, now we're going to talk about an indistinguishability condition between nature and my model of nature. So I want it to be the case that when observers, analyses algorithms, or what we'll call this distinguisher, when the distinguisher is looking at samples that are just labeled as individuals and outcomes, they cannot tell whether the outcomes are being sampled from nature or from my model of nature. So that is sort of the intuitive description of OI. And in fact, we're going to have variants of this that even allow the distinguisher to interact with the program itself, to interact with the model of nature. So even when the distinguisher gets to query, let's say, the model of nature and probe it and look at its behavior, still it cannot make a distinction and make a judgment about whether the sample is coming from nature or from the model which it has full access to. So good. So even more formally, how should we think about these distinguishers? These distinguishers we're going to think about as a class of algorithms. So you can think of these as like, let's say, a class of regression algorithms or a class of time-bounded computations. It's a class of algorithms. Each algorithm is going to take in an individual and an outcome, and it will be basically a Boolean function. We'll map individual and outcome pairs to 0 or 1. And the condition that I want formally, a predictor P tilde is A epsilon outcome indistinguishable if the behavior of every algorithm, A, in my class of algorithms, is the same on samples from nature and from samples from the model of nature. So that's the intuitive definition. Let me formalize this. What do I mean by that behavior should be the same? I mean that for all algorithms in my class, the probability that A prints 1 when given a sample from nature should be only epsilon far away from the probability that it prints 1 on a sample from the model of nature. That's to say that all of these algorithms in my class, their behavior, their acceptance probability on the distributions, on this natural distribution and on the model distribution, should be no more than epsilon apart. Good. Any questions? Anything that is not clear? Okay. So we're actually going to have a few different variants of this notion of outcome indistinguishability. And the variants will vary based on the distinguisher's access to the predictive model. So in particular, the notion that I described on the last page would be so-called no access OI, where the distinguishers only receive individual outcome pairs. Their only access to the model is through these outcomes. This is good. And so what we're going to do is then augment this definition by allowing the distinguishers for more and more access to the predictive model in question, to the model of nature. So in particular, moving up the hierarchy, we see that sample access OI allows the distinguishers access not just to the sampled individual outcome pair, but also to the predicted value, to the predicted probability for the individual I. So in both cases, they get access to P tilde I in addition to their sample. And then finally, moving up, the last notion I want to talk about today, we have some more notions, but the last notion that we'll talk about today is oracle access OI, where the distinguishers will be allowed to query the predictive model on any point that they want. So in particular, they'll be able to run the predictor, P tilde, on individuals who are not I prime, I double prime, to query the predicted value on these individuals. It's not obvious how these escalations should help the distinguishers, but as we'll see, they actually do make a big difference. And so it's important to note that in all of these definitions, the only access to nature that we have is through the outcomes. And this is really where the name outcome indistinguishability comes from, that we're saying that, that the individual outcome pairs should be indistinguishable, even when we allow access to the predicted model. Hey, Parikshit.
Hey, Michael, can I ask you a quick question?
Yes, yeah.
Yeah, so just going back one slide. So we had defined these A's, which kind of only look at one sample and outcome at a time, right? Mm-hmm. And so I guess in the next slide, when you introduce these P tildes, you just extend these by saying that, hey, it looks at this, this, and the third parameter, which is this probability. Mm-hmm. I'm a little confused about how to think about the thing which has oracle access to P tilde. Now, is that still just a Boolean function on the domain x cross 0, 1, or what exactly is?
That's right.
What exactly is it? And the second question, since I'm asking you questions, is that this is kind of like the SQ model, right? Where you just take a single sample. And so does it change significantly if I wanted to be able to look at k tuples of samples and then have some predicate based on that?
Great, good questions. So let me address the first one. Let me try to address the first one. I still want to think. So, okay, I'm using this superscript notation for a p tilde to denote an algorithm that has, access to this p tilde as an oracle, right? So I still think you should think of it as an algorithm that is computing a Boolean function, but parameterized by the oracle it has access to.
But can it be adaptive in,
Sure. Yes. Yeah. So we will allow it to be adaptive. We will allow it. Yeah. I mean, I think you can define it in terms of, yeah, any, like an Oracle Turing machine, an Oracle circuit, like some sort of model like this, where it is allowed to query p tilde. It's allowed to look at the individual it's getting. It's allowed to query p tilde. It's allowed to look at the individual again or look at the responses and make new queries to p tilde. Yeah, so full adaptivity. And then good. So then the second question you had was about single sample versus multiple sample versus, I'm not sure entirely about the connection to the SQ model, but the certainly we can define a multi-sample variant of this as well. And for most levels of the hierarchy that, for sufficiently expressive classes, then we can run a hybrid argument and get sort of a conversion from to achieve multi-sample. Did that help?
Yeah, thanks.
Great.
And Michael, can I ask a follow-up question?
Mm-hmm.
I think this is about the same, it's between the two questions Parikshit asked. For the oracle on the next page, this is persistent noise, right? If I query p tilde in the third line, if I query p tilde on I multiple times, like I can't just adaptively keep querying it and actually uncovering p, right?
Right, good. So actually, that's a great clarifying question. So p tilde, we will think of it as, so let me go back. Good. We will think of p tilde as a predictor from, as a function from individuals to probabilities. So I will reveal to you in full what I think the probability is.
I see. So it's not a draw of that part.
It's
it's not the Bernoulli one.
So
okay.
The only time I'm drawing is when I am getting a sample. So that's a really good clarifying question. So here, this draw O tilde I will be a Boolean draw from in 0, 1. And the point somehow, so I think maybe it's clearest at sample access level. I'm going to show you what I think I'm going to draw an individual and tell you what I think the probability of this individual is. And still, then you're going to see a Boolean outcome. You're going to see a 0 or a 1, and you have to decide whether the 0 or the 1 was drawn because it came from nature or because it came from the model, right? So I tell you that I think the risk is a 0.8, and then you see a 1. And so you have to decide whether that is more likely because of nature or because of the model.
Okay, thank you.
Yeah. Cyrus, I can't hear you. I can see that you're talking, but.
Can you hear me now?
Yes.
Wonderful. May I ask, is this no access AI model, OI model, is there a relationship to, the 0, 1 loss and whether or not you're able to learn something epsilon accurately to the Bayes risk?
So that's a good question. We will see a connection, but it won't be exactly to the 0, 1 loss. Yeah, it'll be a little bit weaker.
Thank you.
Is there difference between this framework and like IPM-based distribution testing? Like the no access OI looks like 2 sample testing, and sample access OI looks like 1 sample testing.
Oh, I'm not familiar. We can chat about it
Okay.
afterwards. Yeah, thanks. Okay, good. So I want to just briefly muse on the fact that like this idea of indistinguishability, hopefully it's not new to everyone. It's a very classic and fundamental notion that we're drawing from the field of cryptography, from pseudo-randomness, where often we talk about computational indistinguishability, where we want to be able to generate samples from some, let's say, low entropy distribution that really look like, that behave, that cause the algorithms to behave in much the way that the uniform distribution would cause them to behave. And so I think there really is a strong analogy between computational indistinguishability and outcome indistinguishability, where rather than randomness being in the eye of the beholder, we'll think of probabilities as being in the eye of the beholder. And really the goal here is to come up with simple generative models that look like nature to all computationally bounded distinguishers. And really, it gives us hope that learning individual probabilities may be meaningful, even if we can't recover the true model of nature. Good. So I'm running a bit slower than anticipated, but that's fine. So we should talk now about, we have this nice definition that hopefully we all have some intuition about. Can we actually achieve it? And to achieve it, the first observation that we're going to make is that there's actually a very strong connection between these variants, some of these variants of OI, to this work on evidence-based fairness, and to these notions of multi-accuracy and multi-calibration. And so to recall, what are these notions? So the more basic notion, multi-accuracy, asks for simultaneous accurate expectations across a rich class of subpopulations, which will denote C. So in particular, for each S in C, for each subpopulation in our class, we want it to be the case that the expectation of the true outcome is equal to the expectation of the modeled outcome. Good. Multi-calibration takes this a step further by requiring calibration across these subpopulations, where calibration is an unbiasedness condition as well, but it further conditions on the predicted value. So it says that my expectation of the outcome should be equal even within subpopulations and after conditioning on my predicted value. So that's to say that when my predicted value is V, the true expectation should be equal to V. Good. So the first theorem that we have says that there is a strong computational equivalence between these notions. In particular, the first level, no access OI, is computationally equivalent to multi-accuracy. And the next level, sample access OI, is equivalent to multi-calibration. And so what do I mean by computationally equivalent? Well, we have statements of the form, for any collection of subpopulations, there exists a class of distinguisher algorithms such that A sample access OI implies C multi-calibration, and in the other direction as well. So to give a flavor for how tightly connected these are, we'll go through the construction for multi-accuracy. So that's to say that we're given a subclass of subpopulations. What we'll do is for each subpopulation, we're going to construct a distinguisher that takes an individual and an outcome pair, maps it to 0, 1, and we'll see that if you satisfy no access OI, then you have to be multi-accurate. So what is this distinguisher class? So I'm going to say that I'm going to define this AS as on input I and OI. First, I'm going to test, is I in this subpopulation S? And then, is the outcome equal to 1? If both of these conditions pass, then I'm going to accept. I'm going to print 1. else I will reject, print 0. So we can functionally write this distinguisher's behavior out as the indicator of I and S times OI, times the outcome. And if we stare at this the right way and use Bayes' rule appropriately, we see that actually the probability that this distinguisher accepts can be related, is proportional to the expected outcome amongst individuals in this subpopulation. So it gives us a handle on this subpopulation expectation, which is to say that if we manage to equalize the probability of acceptance in the natural distribution and in the modeled distribution, then the expected outcomes must be the same. Therefore, if we enforce this for all AS in our collection, then we would get multi-accuracy. We would get this subpopulation expectation guarantee on all subpopulations in our collection. Good. So the construction for multi-calibration is very similar, and I'll skip over this. So using this equivalence, we can then say, hey, we have, in this earlier work, we have algorithms for learning multi-calibrated predictors. So automatically then, we should be able to apply our reduction, reduce the problem of learning an OI predictor to learning a multi-calibrated predictor. And indeed, you can push this theorem through and show that there exists A epsilon sample access OI predictors whose complexity scales as 1 over epsilon squared times the complexity of your distinguishers. So here I'm using time t as a measure of complexity. Most other reasonable measures of complexity also work as well. Further, this construction the theorem is constructive. We actually have an oracle efficient algorithm for learning these predictors. The main algorithmic contribution of this work, though, is really pushing beyond multi-calibration and showing that at each of these levels and some others that we defined in the paper, we actually get upper bounds on the complexity needed to compute OI predictors, that we can learn OI predictors from data. And so what does this theorem say? It says for any nature and any epsilon greater than 0, suppose that A is a class of distinguisher algorithms that runs in time t. Then we actually have A epsilon OI predictors that run in time for no access OI and sample access OI. They run in time t by epsilon squared. For this higher level oracle access, we get t to the O of epsilon squared, so not as good. Importantly, though, it's important to note that this works for any nature, right? So we're not making any assumptions about nature. Nature may be arbitrarily complex. And what we're saying is that for these first two levels, at least, we have good upper bounds. We have sort of efficient constructions despite the complexity of nature. So you can construct a model that looks like nature to these forms of distinguishers, even with complexity that's polynomial in t and in epsilon. And so staring at this a little bit more, you see that the first two levels, really we do get efficient constructions, kind of the best you would hope for. We get linear dependence in t and polynomial dependence in 1 over epsilon. In this upper level, unfortunately, we see that we only get we get an exponential dependence on 1 over epsilon. And so this isn't as good as we would hope. And the question is whether we've somehow been lazy and we really could improve this if we only worked a little bit harder, or whether there's some reason for this gap. And so that's kind of what we'll discuss next. When we allow our predictors, or excuse me, our distinguishers to have oracle access, what happens? How much more powerful are these distinguishers than the sample access or the no access distinguishers? And so the conclusion is actually specified through a lower bound that we show. in fact, there is some inherent reason why we would expect these predictors to be less efficient. So what is the theorem that we show? We show some conditional hardness. We say that there exists a nature and a collection of oracle distinguishers that are efficient. They run in time t, let's say, such that any predictor that manages to satisfy oracle access OI with respect to this class of distinguishers needs to run in time t to the 1 over epsilon in order to even evaluate this predictor. So literally the predictor's complexity, the circuit complexity of the predictor needs to scale exponentially with 1 over epsilon. And this hardness is based on a computational conjecture. It's actually a fairly conservative fine-grained complexity conjecture about the hardness of counting k-cliques in an n-known graph. Feel free to ask me questions about the specific hardness later. Good. So the upshot, though, the point is that somehow if you were able to significantly improve on our upper bound here, if you're able to bring this down to some polynomial dependence on 1 over epsilon, then you get a breakthrough in complexity that we really don't expect anytime soon, or even that it should exist. Good. So at a high level, this shows that oracle access distinguishers somehow give us a very different flavor of indistinguishability than the indistinguishability that we got from no access or sample access, and correspondingly from multi-accuracy and multi-calibration. And so the intuition is that these oracle access predictors really are more powerful because they can inspect the predictions across other individuals. And the queries, therefore, allow them to exploit correlations that might exist across different individuals' outcomes across the population. And what we show is that in some cases, in order to fool these efficient oracle distinguishers, you might actually have to learn nature essentially exactly, which is very different than the earlier notions where we said for any nature, even a very complex one, you can get an efficient construction. So before talking a bit about the hardness result itself, I want to talk about sort of how you should interpret this result. I think the way that we interpret it is that kind of as a positive result almost. It says that these oracle access distinguishers are much more powerful than the corresponding non-oracle access. So in practice, we should give regulators the ability to query the models that they're auditing. If these tests that they can run are significantly stronger, then let's go for it. So I think that's a subtle point, and feel free to ask me more questions about it if there are any. I think the main question to ask from a theoretical perspective is whether we can ever hope to get provably efficient oracle access OI. So we show that at the level of generality that we're working for arbitrary distinguishers and arbitrary nature, we show that our construction is nearly optimal. And you probably can't hope to get much better oracle access OI. This leaves open the possibility, though, for domain-specific oracle access OI that could be efficient. So I think a very natural open question is, in your favorite domain, in your favorite application, what conditions exist? What structure exists that you might exploit? Structure for nature, structure for your class of distinguishers, such that you could hope to get oracle access OI in an efficient manner. Good. I see that I have 5 minutes left. I'll unless Juba interrupts me, I'm going to keep going.
I'm not going to interrupt you. I think if you want to get through the rest of the talk and like use the last 5 minutes, and then we can take a few questions online for people that want to stick around, and I think people can always email you and ask you offline if they have more questions.
Okay, I'm going to skip ahead then. If you want, I'm happy to talk about the nuts and bolts of the construction with anyone if they want to hang around. It's a cool construction, so ask me about it if you're interested. But I think I'll use the last few minutes to recap and take questions. So good. So what did we talk about today? Well, we talked about a framework that we're calling outcome indistinguishability. Outcome indistinguishability is useful for understanding the meaning of individual risk scores and to really try to get a better handle on what algorithmic probabilities can really mean. And we introduce a hierarchy of notions based on the access that these distinguishers have to the predictive model itself. And we saw that oracle access and beyond gives somehow a qualitatively different kind of indistinguishability than these simple tests that are typically thought about. In the paper, we discuss further aspects of these issues and extensions. To Parikshit's point, we talk about multiple sample. I think also to Parikshit's point, we talk about sort of the difference between adaptive and non-adaptive oracle access. And we also show some connections to the forecasting literature, which I didn't have any time to talk about, but I think are pretty cool. So one further perspective is that OI really is trying to generalize this work on multi-group fairness. In particular, we saw how it generalizes multi-calibration and multi-accuracy. I think the point, though, is really even in some of these equivalences, the distinguisher perspective is very intuitive. It gives you a way to get a handle on what's happening and what it means to be indistinguishable. I think somehow this is easier to swallow than the definition of calibration, let's say. And so I think it really does give us an interesting lens for exploring further these issues of fairness in learning. So one provocative idea that we have thought about, or I'll say that I've thought about, is that somehow it feels like a fair predictor should be indistinguishable from some ideal predictor. Now, if the ideal is nature, then OI kind of already gives you a handle on this. But if the ideal is not nature, if there's some historical discrimination that's encoded in nature's samples, then maybe we would want to be indistinguishable from a different ideal. I think trying to formalize that and make progress on it is a really interesting question for follow-up work as well. And really, truly, I view the biggest contribution of this work is setting up the OI framework. I think it's a very nice way to get a handle on certain issues. And I think there are many possible extensions to your favorite application domain. So,
faisons comme ça.
So yeah, I'll stop there and I'll take any questions. And yeah, thanks.
Well, thanks a lot, Mike. Thanks for giving the talk. It was a great talk. Thank you. And I want to applaud in person because, you know, sometimes when you just only have the applause on Zoom with the small smiley, it's hard to see and you don't have the same, you know.
I'll try to expand the,
But yeah, so if you, so by the way, it's almost 1. So I think we have time to take one question before people want to leave. But if you want to leave anytime, and if you have meetings,
yeah, feel free to leave. I'm happy to stay on if anybody wants to chat more.
But if people want to stay on a bit more and ask more questions, that's great too. I see there are questions. So Nika, do you actually want to go ahead?
I have a question, but if somebody else wants to go ahead, I'd rather they go because yeah, if somebody else wants to go first. Okay, if not, let me ask this very, very cool framework, very cool talk. There's something about the runtime that is not working out in my mind, and I'm just trying to understand if you can tell me anything before I read the paper to help me.
Mm-hmm.
So my intuition and understanding is that the way I would do this algorithmically is I have some P. I take an like very similar to multi-calibration, this kind of multiplicative weight update. I'll get an algorithm that's distinguishing beyond what it should be distinguishing in its class. And then I use that to improve my P, and I will do this multiple times. I don't know if this intuition is correct, but if it is
You're on
correct,
the right track.
okay, if it is correct, how are you going from the fact that algorithm is coming from a T runtime class to saying that within a T over epsilon square runtime, you're doing this? Like that selection of an algorithm between all the distinguisher is the part that's not translated.
So this is kind of the hardest point, I think, to talk about, is that when I say, so when I say that the time, this time is the time it takes to evaluate the predictor. It's not the time to learn the predictor.
I see.
So the point is, like, I think the point is, maybe an easy way to say it
you're
is
solving the auditing problem, and if you have the access to choosing the algorithm, you're solving the learning problem. Is that now a fair way to say this?
The point is, I'm not even talking about the runtime of learning here. Like, runtime of learning could be awful. Like, we have ways to improve it in the same way that we improve it in multi-calibration. But like, the point is that the output of your algorithm, maybe you should think of this as the
circuit
size of the output.
Okay.
That somehow the circuit that you're producing that computes this thing is polynomial in this case and is exponential in this case.
Okay, that makes, yeah, the circuit
Thanks,
size is
thanks
a
for
very
that
helpful comparison.
It's an important distinction.
Thanks. I have to head out, but thanks for the talk. It was really cool.
Yeah, thanks. Maybe we should stop the recording, and I'm happy to hang around.
Yeah, sure.